we're delving deeper into limits. And so before we were looking at a limit from a graph or by using direct substitution. So remember, if a function is continuous, we can use direct substitution to find the limit, because the definition of a continuous function is that the limit from the right and the limit from the left equal the function value, which makes sense, right? If you're going from the left, you can just, the limit as it approaches that value, then you can go right through the value and then keep on going, and the limit from the other side equals that. That's what a continuous function is. So when we have a continuous function, we can just plug in the function value and it tells us the limit. But what happens when we have a function that's not continuous? And when we try to plug in direct substitution, we end up with a hole or an asymptote or something like that. So we're going to take a look at that today. What I'm going to do is I'm going to make a quick and dirty video about how to do some of these. I'm just going to do like one problem from each unit, and we're going to go quick to get an introduction. Then I'll make another video or two where I go really deep into it and I explain them step by step. And so if you only need the quick video, go for it. Try the examples on your own. If you want to go deeper, you can watch the deeper videos so you can understand step by step. I would highly recommend watching those, but this will help you get an overview of what we're talking about. So here we go. We have this first problem, and you know from pre-calculus, because you guys are so incredibly smart, which is true, that this function has discontinuities at two places, right? You know that this has a discontinuity at x equals 0 and one at x equals -1, because those would make the denominator 0. And you also know that because this cancels out top and bottom, that this is a hole and that this is an asymptote. Okay? So what happens when I try to do direct substitution, which is always the first choice, always, always, always when you're trying to algebraically evaluate a limit, do direct substitution. If direct substitution does not work, then we use these methods, okay? So we know there's a hole at 0. So I know what's going to happen when I do direct substitution, right? I'm going to plug 0 in, and I'm going to get 0 over 0 times 1, which is 0 over 0, which is called the indeterminate form. And I can't divide by 0, so there's a problem, right? So when I get this indeterminate form, or when I get dividing by 0, I can't just use direct substitution because the function value doesn't tell me the limit. I know what's happening with this function. I know that it's going along and then it's got a hole and then it keeps going. I just need to figure out where that hole is. And you guys actually already know how to do this. We're just going to do it in the form of a limit. So what we know about the properties of limits is that the limit as x approaches this whole function is the same as the limit as x approaches 0 of the reduced function. So we cancel out those x's and we end up with 1 over x plus 1. Well, what's the limit as x approaches this? Again, let's try direct substitution because this is a continuous function, so I can use direct substitution. And when I do that, that equals 1 over 1, which equals 1. So the limit as x approaches 0 of this function is 1, and because of limit rules, I know that the limit as x approaches the original function is also 1. Now you know that from pre-calculus because you know how to find this hole, right? You know that when you cross out those x's, that you find the coordinate of the hole by just plugging in 0. So when I plug in 0, I know that I have a hole at 0, 1. So that's how we know that the limit is 1 as well. So let's look at another type of problem. We're going to discuss the continuity of this piecewise function. If my computer ever catches up, there it is. Okay, so this says that when x is not equal to 3, we're looking at this function, and when x equals 3, we're looking at this function. So let's figure out what these functions are. Okay, the first one, the top one, let's factor it, and we get x minus 3 and x plus 1 over x minus 3. That's our top part of the piecewise function. And so we know that it is discontinuous at positive 3, but because they cancel out, we know there's a hole at x equals 3. Oh, isn't that convenient that that's also where our piecewise is? Weird. So then we know what happens is that this graph actually looks like the reduced function. It looks just like this function. The only difference is it has a hole at 3 instead of being continuous at 3. So, well, what does that function look like? it's actually a line. X plus 1 is a line with a slope of 1 that goes through the point 0, 1. But at x equals 3, there is a hole. And then what is happening at x equals 3? Well, this piecewise tells us that when x equals 3, y equals 5. Okay? So what I have to decide is that hole, or is this 5 right here, or is it up here? Let's find out what's going on. So we're going to look at the limit as x approaches 3 from the left of x squared minus 2x minus 3 over x minus 3. And then we're also going to look at the limit as x approaches 3 from the right of x squared plus 2x minus 3 over x minus 3. And see what's going on. Where is that hole, right? It's at 3, we know that. So what's going on here? We know that that cancels out, top and bottom. So we can plug in 3 for x plus 1, right? And so this is 3 plus 4. So since this cancels out, it's the same as the limit as x approaches 3 from the left of x plus 1, which is 4. And the limit as x approaches 3 from the right of x plus 1. Since it's a hole, it should be the same. They should be approaching the same number, right? That it's at 4. So we know that the hole is actually at 3, 4. And we know that this extra piece of our piecewise function is at 3, 5. So now we have to discuss the continuity of this. So let's use our math terms to decide what's going on. Well, we know there is a hole at x equals 3, 4, but we need to be a little bit more specific. We need to say, is that a removable discontinuity or non-removable discontinuity? Well, remember, a hole is a removable discontinuity. So we can just say that this has a removable discontinuity at x equals 3. And that's it. That's the only non-continuous part of this function. All right, we're going to use the calculator to find these limits. So let me pull my calculator up. So when we put this function in the calculator, remember that you need to put parentheses around the entire top and parentheses around the entire bottom so that your calculator knows what's on top and bottom. We're going to go ahead and graph this. And we're looking at the limit as x approaches 1. So this is actually really easy. Sometimes we might need to use a table to look at it, and I'll show you how to do that. But look, it's got an asymptote. Done. There is no limit because one is going to positive infinity and one's going to negative infinity, so it does not exist. You could look at the table, so let's go to the table, second table, and we're going to look right at 1. When x equals 1, it says, error, it can't figure out something. So let's change our table, second table set, and we're going to start our table at 1, and we want the change in the table to be 0.01. So we want just a tiny bit on either side of 1 is what we want, and then we're going to graph it, or not graph it, sorry, go to the table, I pushed the wrong button, the table, and you look what's going on. As we get closer and closer to 1, we're getting huge. And as we get closer and closer to 1 here, we're getting bigger in a negative way. And then we have an error at 1, which is our asymptote. And if we change our table settings even more, let's get even closer. We're going to go 0.0001. And we're going to start the table at 1. So we're going to look at our table. And look, you can see that as you get close to 1, this gets huge in the huge numbers, and these get huge negative numbers. So even if you can't see the asymptote on your graph, you can actually see on the table that there is an asymptote. So this limit does not exist. Last but not least, we're going to talk about the intermediate value theorem. Very important theorem. Write it down. Make sure you understand this. We have lots of different theorems with lots of different names. This is one of our first ones. So the intermediate value theorem tells us that if a function is continuous on this interval a to b, if it's continuous from a to b, and there is some value that is in between f of a and f of b, meaning the y values of our function, then we are guaranteed that there is some x value that will spit out any y value on that in between f of a and f of b. So let's look at an example to understand what this really means. So we're asking, does the intermediate value theorem guarantee a c value on the given interval? So this is a function x squared minus x on the interval 0 to 5. The first question you need to ask, is this continuous on 0 to 5? So we need to check our conditions, and we need to check, is it continuous? Yes, this is continuous because there are nothing illegal, right? There's no domain restrictions. So number one is we have to write f of x is continuous. So anytime we're checking with the intermediate value theorem, we need to satisfy all conditions, and we need to show that we satisfied all those conditions. So we actually have to write down, yes, I satisfied that condition, f of x is continuous. Number two, the next thing is, oh, I'll underline these. This is number one, f of x has to be continuous. Number two is that there is some k value in between f of a and f of b. Then number three is our conclusion, okay? So it says, I'm looking to see, is 12, is there a value in between, is there an x value in between 0 and 5 that gives me 12? That's the question. That's what the intermediate value theorem is asking. So we have to decide, is there a value in between 0 and 5 that spits out 12? So the first thing we had to see is f of x is continuous. Now we have to check, is 12 in between f of 0 and f of 1? Right? Because it has to be in between f of a and f of b. That's our second condition. Let's check to see if it is. Well, f of a would be f of 0, and f of b would be f of 5. So we plug 0 and we get 0 squared minus 0 equals 0. Okay, so f of 0 equals 0. If we plug 5 in, we get 25 minus 5, which equals 20. Okay, so now we have to see, is 12 in between? We're looking at to see if this y value is in between these two y values. And we can, again, we have to show that we checked this. F of a is 0. It is, in fact, less than 12. And 12 is also less than 20. So yes, 12 is absolutely in between 0 and 20. Therefore, condition number 2 is met. So our final point number 3, would be that the intermediate value theorem guarantees that there is a c value in the interval 0 to 5 such that f of c equals 12. Because our other two conditions were met, it is continuous, and 12 is in between f of a and f of b, we absolutely guarantee by the intermediate value theorem that there is a c value somewhere. There is some x value in between 0 and 5 that will spit out 12. Does that make sense? So then we could check for that c value. It doesn't ask us on this one to find the c value. Oh, that's on the last one. I'll go ahead and do that. It says find the c value of c in example 9a. So we say there is some number that when I put it in, it spits out 12. So then y would be 12, right? And then I just have to figure out x squared minus x. When would x squared minus x equal 12? Well, this is a quadratic. To solve it, I need to get 0 on one side, and then I need to factor it. So I get x minus 4 and x plus 3. And so my solutions for this that would make this one true, that would make this equal 12, are 4 and negative 3. And so you're like, cool, 4 and negative 3. But wait, there's more. Which one of these values is on the interval 0 to 5? Just this one, right? So the c value that spits out of this function, 12, is 4. So if I put 4 in, it spits out 5. And the intermediate value theorem guarantees that. The reason we care about the intermediate value theorem is because it guarantees zeros. It guarantees zeros. That's the most important reason why we care about this. Because imagine you have this continuous function, and this one's above the x-axis, but say we have this function and we're trying to figure out, is there definitely a 0 in between this number and this number? I'm going to move the x-axis on this one. Let's say the x-axis is right here, okay? And I say, hey, on this interval, is there a 0 between here and here? Well, if a is negative and b is positive, and it's continuous, it absolutely has to go through 0 to get from negative to positive, right? So the intermediate value theorem helps guarantee